Okay, so today we're going to be covering survival analysis, which is something that comes up pretty often within medical research. So we thought it was an important topic that was and worthy of a session on it. So how this session is going to unfold is that I'll give a bit of background information on just what it is as a concept, when it's applicable to use, as well as some certain terminology that's important. And then we're going to delve into some of the methodologies listed here, Kaplan-Meier curves. If you want to compare two curves, the log rank test, and then if you want to introduce other variables into your model, the Cox proportional hazards model. And as we go along, Roland is going to be guiding us through some application exercises in R as we go through the PowerPoint. Okay, so just first off, what is survival analysis? I was going to have a quote here, but didn't find anything compelling. So if you have a favorite quote on survival, definitely throw that down in the chat. So just as an overview, so survival analysis is sort of a basket of methodologies and that are used whenever you're interested in looking at longitudinal data, where what you're interested in is the time until some event. And that's sort of the key, is the time until an event. So some examples, so death due to COVID-19 from the onset of symptoms, the time until an HIV positive patient becomes AIDS positive, or it also does not have to be medically or death related. So it could be the time until a iPhone malfunctions due to bloatware that Apple includes in all of their updates. Okay, so some of the use cases for survival analysis. So estimating the time to event for a population of individuals. So time to event just means the time from the start of a study until the event of interest. And for the time to event, we're going to be looking at Kaplan-Meier estimator. That's a very popular one to use. And then if you want to compare the time to event between two groups, as I said before, we're going to look at the log rank test. And then for assessing the relationship of covariates on time to event, that's where the Cox proportional hazards model comes into play. And so those are kind of the three use cases that we'll be looking at today. Okay, so here's just a sample case to sort of get your brain thinking. So what we have here is a graph from the Johns Hopkins coronavirus dashboard. And this is the great state of Texas that we're looking at, just the number of cases per day. As you can see, been increasing in the past. I think everyone knows that. And so here's just a sample thing. So perhaps physicians at Ben Taub are interested in knowing what the time to discharge is when patients present to the ER for COVID-19 symptoms. And say that they're also interested in factors such as age, gender, and existence of pre-existing conditions. So one thing that you may be asking yourself is, okay, so we have a numeric dependent variable in the time to discharge, and we have these other covariates, age, gender, and presence of pre-existing conditions. So why can't we just use a normal multinomial regression model? Why do we have to use a specific survival analysis methodology? And the answer to that is that not everyone is going to be discharged, right? So unfortunately, some people are going to could die in the hospital. So how do we handle those cases? And perhaps one idea you could say is, okay, so maybe we then create some type of multiple logistic model where we predict, death in hospital versus being discharged. But the problem with that, of course, is that then you lose the time aspect that you're interested in. So that's really the need for survival analysis methodologies. Okay, so now I'm going to cover some terminology that's frequently used when discussing survival analysis methods. So one of the biggest concepts to understand is the idea of censoring. And all that is a statistical word that is used to just describe incomplete data where you don't know whether or not the event that you're interested in has occurred. And so that can take the form of left censoring, interval, and right censoring. So left, interval, right, but mainly you'll come across right censoring, and so that's the one that we're going to focus on. And so right censoring can occur in 3 ways. So if we're unable to follow up with an individual, so say they're on they're in a study, you've enlisted them, and perhaps their phone number changes and their address, and you're just not able to get a hold of them again. So basically, you have no way of knowing whether or not, say you're interested in myocardial infarction. You have no idea whether or not they experienced that event. They could withdraw from the study, or the study could end prior to the event occurring for them. And so that's illustrated over here. So obviously in medical studies, right, we can't take forever for this, the duration of the study, right? You can't spend 50 years waiting for someone to get a myocardial infarction. So you have to draw a line somewhere, you have to set some boundaries in your study design. So inevitably, some people are just not going to experience the event prior to the end of the study. So that's what it means, and those individuals would be censored. So that's displayed here. So they reached the end of the study, let's say it was a 4-year study, and they didn't experience the event. And this person, maybe they withdrew from the study or we weren't able to follow up with them. But then all the other individuals experienced a myocardial infarction during the time duration of the study. Okay. And the other, another concept that I want to put in your brains is this idea of a survival function. And all that is it's like any other sort of f of x function that we covered in high school and calculus. So you have an input, and then the output is a survival probability. So you have some specified input, and then the output is always going to be the probability that the subject will survive beyond a specific point in time. So here's, for completeness sake, the general formulation of a survival function. You don't really need to focus in on this. The reason I'm putting it in is just to highlight the fact that the survival function, so this probability that the subject will survive beyond a given point in time, is dependent upon the previous time periods. So obviously at each time point, you're going to be given a new survival probability, and it's dependent on the previous ones. So that's easier to understand here in a graph format, okay? So what we have here is the cumulative distribution, which just means it's a summation of all the survival probabilities up until that point, okay? So these up until 100 hours, the summation of the survival probabilities up until that point is 0.81. So what's the probability that you survive beyond 100 hours? If we go to this graph on the right, it's 0.19. So it's just, we go back and we look at the formulation, it's 1 minus this f of t is the cumulative. And so that's all it is. So basically, surviving beyond 100 hours is dependent upon everything that's happened before. That's the takeaway here. So that's what I really want to ingrain in you, is that it's just dependent on previous probability, the previous survival probabilities. And don't worry about the formulation. Okay, so from the first section of slides, so the key sort of takeaway is that survival analysis is just a sort of term that describes methodologies that looks to estimate the probability of surviving to or past specific point in time. And that's sort of just the highlight takeaway. Okay, so now we're going to discuss our first methodology, and that's the Kaplan-Meier estimator. And as stated before, the Kaplan-Meier estimator is used whenever you're interested in determining the probability of surviving past a particular point in time, t, we'll call it. Okay, and okay, so what does it mean by non-parametric, right? Okay, so non-parametric just means that it's not reliant on an assumed underlying distribution. So we're all familiar with the normal distribution, so let's just, for simplicity's sake, it doesn't have to be a normal distribution, okay? Okay, here's the formulation for the Kaplan-Meier. Again, don't focus on, you know, this mathematical form, but the takeaway that I said in the survival function is that it's dependent upon previous points in time. And that's just reflected. This is a product symbol, which just means that you're multiplying together all the previous probabilities. So that's all this is doing, is up until, let's say, time point 5, you're multiplying the probabilities of surviving from time points 1, 2, 3, and 4, and 5. And that's essentially all this formulation is saying. So again, I don't want to get bogged down in the mathematical formulation. It's more about the intuition. Okay, so assumptions for this model are that at time 0, your probability of surviving is 1, right? That's intuitive because it's the start of the study. Okay, and number 2 here is probably the most important. So survival probabilities are the same across all subjects. So if for some reason, and if you're ever in the future and you're wanting to do a study design and you have reason to think that this is not the case, then Kaplan-Meier would not be an appropriate methodology to use. So this is sort of a simplifying assumption that the model makes, but it's important to first verify that this is true. So, because a lot of times, especially go to—
Can you give an example when that'd be violated?
Yeah, sure. If there's a population, say we're looking at probability of, say, time to develop AIDS if you're HIV positive, and you have perhaps included in your population are both, let's say, homeless and non-homeless people, and that's included in your population pool. Obviously, that's going to be a pretty large factor, and they're not going to have the same access to care. So the probability, the survival probabilities, and probably rate at which that occurs, because, you know, even though they're both immunocompromised, one may be able to afford medication or not. So those probabilities, those curves probably do not look the same. Okay, so the third assumption is that events happen at the time specified. So that just kind of means that it's like discrete. And then censoring, what we discussed, where you have incomplete data where you don't know whether or not the event occurred. This is unrelated to prognosis. So censoring, just because someone is censored in your study, that doesn't tell you whether or not they experienced the event. So for all we know, they may have, or they may have not. So, and then limitations of this methodology are that it doesn't control for other variables, if you want to include those. And then it requires categorical predictors. So what does that mean? So for instance, of the AIDS example I just gave, you could split that up into a homeless and non-homeless population. And then you'd have 2 curves for each of those populations. Okay, and so now Roland is going to, I think, do an example in R for us.
Let's do it. Okay, I'm going to take over the screen. Can everyone see that? Is that black too annoying there? Black and blue?
I can see it.
Okay, great. All right, so Paul actually mentioned this to me. This week I'm not gonna give just like a blank worksheet because some of the code is a little bit more in depth, and I just wanted to give you examples that you can then see how to kind of plug and play with. So the data set that I have access to that I sent y'all in the CSV file is just some breast cancer survival data. It's not a complete data set. It does have 500,000 patients. I had to cut it down so that no one could just take it and publish on it on their own. I'm just kidding. But yeah, so that's that. But in it, you'll see there is survival information for breast cancer patients based off of all kinds of things. You know, you can look at their tumor type, whether they receive chemotherapy, et cetera, et cetera. And we'll have two different survival outcomes. So first, if you want to follow along with me, it's all in the email. You can open this R Markdown and follow with me. So in the first section, I've commented out the install packages survival. If you've never installed this package, I would just uncomment that out. But the OS event is 0, meaning that at the time when this study was concluded, this patient 1 had survived 57 months without dying. So we don't know when they die. All we know is that there was 57 months that they didn't die. And the nice thing about Kaplan-Meier is that it accounts for that, and that doesn't actually end up skewing your data. It's just known as right censoring that goes as part of the Kaplan-Meier. So then if we go over here, there's all kinds of other different interesting things we can look at. They've got age, the grade of the tumor at onset, stage, TNM score, which this is tumor nodes, metastasis indicators, hormonal receptor positivity, whether they receive chemotherapy or not, whether they receive radiation or not, okay? So going from there, we can do our Kaplan-Meier survival curves. And this might seem like a lot of code, but I want to walk you through it. The survival library gives us some functions that we can use to perform Kaplan-Meier analysis. So the first thing we would do is this little hashtag part of code, which would be to just run a survfit function to calculate survival, okay? So .survfit is just the object that I'm naming for this analysis. So you can see I'm putting an arrow here to name .survfit, okay, like a model. Then I'm gonna run a survfit function. So there's some other further functions on top of that, serve, okay. Then for in the serve function, you have to designate what is your column or your variable that would be indicating time into the event, and then what is your event indicator, right? So you've got two things. This one would be a numeric, like integer, right, months. This one would be kind of like a yes, no, okay? So we're gonna look at survival time in months until overall survival, so death, with respect to ER status, okay? So if we just typed in serve time, serve OS event, that would give us one curve that said for the whole population, here's how long it took for everyone to die, right, or be censored. But if you put the little tilde, it's almost like putting like a Y in your function. You're saying, how does this compare with respect to Y? This variable allows you to create multiple curves based off ER status. So we're gonna create curves based off of whether they have different ER receptor hormone positivity. I've just included some other points in here just for your reference. I don't wanna kind of just drown you at once, but confidence type would be log. Confidence interval, I'm putting as 95% confidence intervals. This just means that confidence intervals will display on our graph. Our type's gonna be Kaplan-Meier, like we discussed. Error, there's several types of error, Greenwood is fine. And then you just say data is equal to survival data. So this is that input data we loaded, okay? And then what I just call my model by itself so that it will show up. So I can highlight all of this, and you can too, and hit run, okay? So what did that do for us? That created a model, just like any other f of x model, that will predict survival at any given time point. A summary of that is printed out here in the drop down or here in the console window. You can see that our results are stratified by ER status, like we liked, meaning there's borderline negative, positive, or unknown ER status. You can see the number of persons in each group, the number of events that were captured, and then median and 95% confidence intervals are not fully populated here, but that's not super important. So what can we do with this? I mean, I think the iconic thing with the Kaplan-Meier analysis is to get some really pretty curves like you'd see in NEGIM. So we can plot it, okay? So that's the next block of code here would be plot, which is just a general R Studio way to plot models or other types. So serve fit as a model here. I have a few little kind of formatting ideas just to make sure the formatting looks good. I've included what those mean here and a link at the bottom if you would like to read more. If you put confidence intervals equals true, that will show your 95% confidence intervals on the graph. And then more formatting, I just labeled what I want my X label to be, my Y label to be, where I want my legend, what all I want my legend to say, the title of my legend, and then the title for my overall graph. So some of y'all are probably working faster than I can talk, but if you do this, you end up with a nice Kaplan-Meier curve. So as you can see, survival as months go by decreases based off of survival type. So you can see there's black, which is borderline, ER negative would be red, ER receptor positive would be green, and then blue would be unknown. Of note, you can see these little black lines around the outside. Those are the 95% confidence intervals. Since this is such a big data set, you can't, the confidence intervals are very small for the green, the blue, and the red. And the only one that has a small enough kind of in to where the confidence intervals are wide is this borderline. So with fewer patients, you would see little confidence interval lines outside, which if you can kind of think like a t-test. If the curves and the confidence intervals don't overlap, it's probably pretty likely that those curves would be significant in terms of survival that you observe. Just a few other lines of code before we get to the presentation. If you want to view quantiles, you can view quantiles. If you want to view the exact summary information, there's a summary function. You just run summary of the original survival fit model that you put up top. And that's kind of cool because that shows you in your console or in your R commando dropdown or markdown dropdown exactly the time to event. So it's a lot of information, but you can see here that for those that had estrogen receptor borderline, exactly kind of how the Kaplan-Meier works. So at time 0, there were 586 persons in the study who had ER status borderline, okay? At that time frame, there were 8 persons that died. So 586 that were at risk, 8 died, that gave a 98.6% survival, okay? And then you can see how it drops down to time point 2, month 2. Now we have 586 minus the 8 people that died. So in our population, we have 577 that reached month 1. And at that month 1 mark, 7 died, okay? So you can see that the number at risk are basically the number at risk previous minus the number who experienced the event. And then at each time point, you just end up calculating the ratio of how many people experienced the event out of the new total population pool to get your survival percentages as they go down. So this is a good way to understand what Kaplan-Meier is doing is you're just constantly reevaluating the survival percentage at the time point in question. You can view medians or just more summary statistics, kind of like what you saw originally here. And then ultimately, if you want to make a bunch of models and just call them all the same thing, you can remove .servFit so that you can create a new model. We made our model with respect to ER status. I've had to make a bunch of models, so I just included them all here for you. They're the same idea, but this one would be progesterone receptor status, tumor grade, whether they had chemotherapy or not, and tumor stage, just so you can kind of see what all, how manipulating those variables will work. So quickly you can see how survival is impacted by progesterone receptor status, by tumor grade, by whether or not someone received chemotherapy or not, and by initial starting stage. So as you might expect, stage 4 tumors have much a greater hazard compared to stage 0 and stage 1. So with that, that's the introduction to the Kaplan-Meier curves and some code for you to do it. I'll turn it back over to Corey to continue with how do we prove although these look pretty dramatically different, how would we prove that these two are actually significantly different?
Okey-doke. Cool. Thanks, Roland, for that. High level, I know we've given a lot of information so far, but high level for just Kaplan-Meier is that it's used to fit a survival function that you can then use to predict the survival probability at given points in time. Okay. So as Roland mentioned, so if we want to determine whether or not two curves or multiple curves are significantly different, the method that we're going to use is the log rank test. So what this is it's a statistical hypothesis test where your null hypothesis is that the two curves are the same. So there's no statistically significant difference between the two curves. And for this log rank test, we'll be generating a p-value from the chi-square distribution. So that's just the distribution, probability of distribution that it pulls from. Okay, and so an important concept for this test is what's known as the hazards ratio. And what that does is that it looks at the number of events, so in each group, over the number of cases, or the number of people in each group. So that is, for each time point, the hazard ratio is just the proportion of people in a group who experience the event, and it's just comparing the two, one group to another. So how that looks from a formula standpoint. So this just indicates, so O indicates that this is the number of observations. N indicates that it's the number of subjects in a group. Okay, and then 1 indicates this is group 1, 2 indicates this is group 2. Okay, so all we're doing is comparing the number of observations in time period J to in group 1 and group 2. So the proportion of cases, and that's all that the hazard ratio compares. And there's a hidden slide in this deck that gives you some of the more nitty-gritty math on this statistic if you're interested in that, but it's really not necessary. And so I've just included it as a supplemental information for those interested. Okay, so the assumptions for the log rank test are the exact same as the Kaplan-Meier, namely that the survival probabilities are the same across all subjects, the events happen at the time specified, and that censoring is unrelated to prognosis. So I'll kick it back to Roland, so that way he can go over how to accomplish this in R.
These next lines of codes are much smaller, so that you already got through kind of the bulk, if you will. But if you just scroll down in your R Markdown that I sent out, you can see that the next little area is known as the log rank test. As we're still using the survival package, you'll see similar kind of coding as what we did before. You might remember serve, with serve time being our month indicator and overall survival being our death indicator, looking at ER receptor status using our survival data. The only new thing is this function called serve diff, the difference between the curves. And so if we run that, it will, kind of like in ANOVA, try to see if there was a significant difference between the curves. Now, if you are familiar with ANOVA, you might, you probably get what I'm alluding to here is that such an analysis gives you a single p-value saying that the chi-squared with 3 degrees of freedom comparing ER status, borderline negative, positive, unknown, was significant. P was 2 to the negative 16th, right? However, all this is indicating is that at least one of the curves was different than the others, similar to ANOVA. So you can do this if you only have 2 curves in question and really get to determine which 2 curves are different. So if I change ER status, which has 4 types, to chemotherapy, which is yes or no, then we'll be looking at the difference in the survival curves only between patients who received chemotherapy versus those who did not. And what you can see here is that now our function SERVDIF compared chemotherapy yes to chemotherapy known unknown, and you could see that the chi-squared observed minus expected yielded a chi-square statistic of 1047, which with 1 degree of freedom was very significant. So this log rank test ends up becoming a chi-square to help you understand whether curves are different or not. So I will send it back to Corey.
Cool. Okay, so again, high level takeaway for y'all is that you can use the log rank test to compare two or more survival curves. Okay, so the last methodology that we're going to be discussing today is the Cox proportional hazards model. And this is a very useful model because it allows you to introduce time-dependent covariates in your analysis. So that way you can see how survival is affected by these covariates. Because oftentimes, you know, there's multiple variables that we're interested in understanding how those variables influence the probability of survival. For the Cox proportional hazards model, as in the name, we're going to be using a hazard function, and then we're going to be comparing the hazard functions for 2 groups. And the hazard function, so what it does is it describes the probability of an event, which is also known as its hazard, for a given subject at time point t, okay? So you can think of this sort of as like the opposite of a survival function, right? Where a survival function tells you the probability that you'll survive beyond the time point t. This is the probability that a subject will experience the event in time point t. So mathematically, it's not the opposite, but that's how you can sort of think about it. Okay, and then this next line, so this is, as I just said, it measures the instantaneous risk of death. All that means, you know, is just the risk of death at time point t. And the takeaway from this little guy down here is that the hazard function and the survival function S of t are related. And if you know one, you can get to the other. That's all that I kind of want you to take away from this little block of text down here. Okay, so this is how the model is written out in its functional form. Again, I'm gonna break it down, each of these specific parts for you, and let's focus in on the intuition and words rather than the mathematical formulation. So this portion right here, H of t, this is basically your hazard risk. So the probability that a subject will experience the event of interest in time period t. Okay. This H naught t, this is your baseline hazard risk. So essentially, like in a normal linear model, right, where you have y, say, equals mx plus b, right, you always have an intercept. And you can think of this as an intercept, where all the other covariates are 0, and what we're left with is just this baseline hazard. Okay, so if all these are 0, e to the 0 is 1, so this is what you're left with. Okay. And then lastly, this portion of it where these, of course, you've probably seen like beta before. That's sort of your weights for each independent variable. So your yeah, so the weights, and these can be interpreted in terms of closely in relative risk, essentially, similar to relative risk. So that's sort of the takeaways I want you just to take away from this model. Is not really to focus on the entire thing, but sort of what each one sort of the idea it represents, so to say. Okay, and so here we have, so HR just stands for the hazard rate, and then so for group, and then these are your different groups. So we're comparing them. So the hazard, this is the hazard function for group I, for group J. And then all we're doing, essentially what I want you to take away from this is that you're just comparing the two, right? So that's the proportional and Cox hazards proportional model. So we've discussed the hazard function, that's where you get the name hazard. And then it's proportional because we're comparing two functions to another. So that's all that this slide is intended to illustrate, is that proportional part. Okay, and so assumptions for this model are that the hazards of the patient groups you compare are constant over time. And so what that really means is that the relative risk is constant over time. Okay, number 2 here, the hazard is a fixed proportion of the hazard for any other individual. So what this means is that the functions, so if we go back here, it means these two functions are parallel to each other. So there's just, and the difference in their slopes can be indicated by this ratio here, this proportion. And then the last assumption is that the other variables that you want to include in your model have to be time dependent. Okay, so now I'll let Roland sort of illustrate this in R.
Sure. So that kind of hazard ratio we mentioned is thought of as the Cox proportional hazards model, which is your last block of code here. Similarly, it is included in the survival package that you downloaded, and basically the same serve kind of input can be used, meaning that you have your time, your outcome, then you can say your kind of your Y variable, your response variable, what you want to include in your model. And this can be multiple things. So the first one I included was just a single univariate model, just for your example. And then you have your comma for your survival data, which is our original data, and we're going to run the Cox proportional hazards model. So if we run that, what we get is coefficient. And so this is saying that for age, that the model was significant. So that age was a significant covariant in the model. You get the coefficient, and then the exponent of the coefficient, if you can imagine, going back into that model that Corey introduced you to. If this is what the coefficient is, then the exponent of the coefficient can help you understand how age impacts the hazard. So this is kind of what's known as the hazard here. If you want to read more about it, there's a link right down here that I thought was pretty good, little online manual, okay? But what if we don't want to just look at how age impacts survival over time? You can say, let's run it with multiple different covariates. So now we have age, stage of the tumor, and the subtype of the tumor of interest. And the cool thing about this Cox proportional hazards model is that you can see about how all of these covariates impact the model at the same time. So as we discovered before, the coefficient for age was significant. You might notice it's very marginally different but a very similar exponent in terms of how it impacts survival. Stage of the tumor, an initial stage 1 does not have a significant impact on proportional hazards here, but stage 2, 3, and 4, their findings were significant. So if you look at the exponent of the coefficient, you can see that a stage 2 tumor had a 2.6 increased hazard, a stage 3 tumor had an 8.9 increased hazard, and a stage 4 tumor had a 45 kind of hazard ratio here. So that kind of makes sense with what we would think logically. Again, stage 1, it says, oh, it has a decreased hazard ratio, but that value was not significant here. Okay, so the p-value based off of the z-statistic. Then we have our subtypes, luminal A, B, normal, triple negative. You might have heard those terms. Everything except for normal-like was significant. So A and B actually had decreased hazard ratio compared to the population as at large, but the triple negative breast cancers, which might be a buzzword that you've heard floating around, did have a increased hazard ratio. So the nice thing about Cox-PH is you can compare a bunch of different covariants at the same time with respect to how they, over time, influence the overall hazard. So hopefully that provided you with some tangible kind of modeling references in terms of how you could run your own survival analysis with your own data. So with that, I'll pitch it back to Corey. Thanks for letting me teach that.
Okay, so we just had a nice demonstration from Roland and R. And so I guess some limitations of this methodology are that you're assuming that the variables are constant in terms of their hazard. And so that certain ones don't strengthen or weaken during follow-up. So Paul, I know you probably want an example, so I'm trying to think of one. Let's see, what's hazard? I may have to get back to you on that, but most of the times the Cox hazard proportional model is applicable, but this is just like one of the caveats. So then the takeaway from this section is that the Cox proportional hazards model allows us to produce survival curves that can be adjusted for other variables in our model. And you can interpret these variables in terms of relative risk. So that's sort of the high-level takeaway from the Cox proportional hazards model. And at this point, that's all we have for you. We did the applications as we sort of went along. So if anyone has any questions at this point, feel free to ask, put them in the chat, and we can hopefully clear up any misunderstanding you might have. Or if no one has any other questions, thank you everyone for attending. And hopefully y'all have found this series of lessons beneficial, and that you feel you are more comfortable emerging from this, working with data in R and taking on some of future analysis that you might have to do. So with that, I will open it up to questions if anyone has any.